Hello, and welcome to our class presentation on the importance of Fourier analysis in gravitational wave detection. My name is Tad, and I will be presenting this with my partner Jared. Today, we will be giving you an insight on how Fourier transforms help us as humans peel back the layers of the universe around us. I'll pass it off to Jared for the next slide.
Hey there. In this image shown here, you can see that an artist's rendition of two neutron stars orbiting each other shortly before colliding. You can see the gravitational waves emitting from their epicenter. But that poses a question. What are gravitational waves? They're not photons, like conventional electromagnetic waves, but rather they are ripples in the fabric of space-time itself. Gravitational waves are generated by the motion of massive objects in space. Whenever these massive objects undergo acceleration or experience a change in their motion, they emit gravitational waves. The most significant sources of gravitational waves in the universe include, but are not limited to, binary black hole mergers, binary neutron star mergers, neutron star black hole mergers, supernovae, and other collisions. Even though they are caused by massive cosmic events, their relative impact Even though they are caused by massive cosmic events, their impact on faraway celestial objects, such as the Earth, is minimal. This makes them extremely difficult to detect.
So here in slide 3, we're going to go over how the waves are detected. LIGO, or Laser Interferometer Gravitational Wave Observatory, and Virgo use laser interferometry to detect gravitational waves produced by highly energetic events in our universe like those described in the last slide. These massive L-shaped detectors aren't like your typical observatories. We use these detectors to measure motion 10,000 times smaller than an atomic nucleus, all from events occurring tens of millions or billions of light years away. The detector's two vacuum chamber arms stretch out 4 kilometers apiece to house the laser beams. The basic idea of the detector is to split the laser beam into two perpendicular arms and then recombine those arms to create an interference pattern frequency. When a gravitational wave passes through the interferometer, it causes a tiny change in the length of the arms, leading to a change in the interference pattern. These signals can be transformed from the time domain to the frequency domain via a discrete Fourier transform, and then subsequently filtered and compared. This method helps improve the accuracy of wave. Jared will walk us through how this is accomplished.
As Tad mentioned in the previous slide, he explained how the LIGO detector is used to generate a signal of all events in order to detect gravitational waves. The signal produced by the gravitational wave passing through the interferometer is relatively weak in comparison to the background noise. In order to extract the gravitational wave signal from the noise, scientists use the Fourier transform. The Fourier transform helps convert the time domain signal obtained from the interferometer into the frequency domain. This process allows researchers to identify the characteristic frequencies associated with the gravitational waves. Scientists then use theoretical models of gravitational wave signals generated by different astrophysical events, such as black hole mergers or neutron star collisions, as templates. These templates are These templates are in the form of waveforms with specific frequency patterns. The Fourier transforms of these templates are calculated and used as a reference in the analysis. The process of comparing the actual interferometer data with the theoretical templates is called matched filtering. By performing a cross-correlation between the data and the templates in the frequency domain, scientists can enhance the gravitational wave signal's detectability and reject noise. After the filtering occurs, scientists apply various techniques to identify significant signals above background noise levels. By studying the parameter of the detected signals, such as the frequency, amplitude, time of arrival, they can infer information about the astrophysical event that produced that particular gravitational waves. In the image on the left, it shows an image. It demonstrates what a signal coming from LIGO may look like, along with the background noise. The pink is the background noise, and the red is the actual gravitational wave signal. And on the right side here, you can see what a filtered gravitational wave signal looks like.
This leads us into our conclusion. Overall, the field of gravitational wave detection relies heavily on signal processing techniques like Fourier transforms and match filtering to reveal the faint signals hidden in the noise and provide insights into the most energetic and cataclysmic events in the universe. The success of LIGO and Virgo in directly detecting gravitational waves in recent years has opened a new era of gravitational wave astronomy, allowing scientists to explore the cosmos in ways never before possible. These advancements would never have been possible if not for the research and applications of signal processing techniques such as the Fourier transform and convolution. Here you can see our sources. I don't know if we need to add that.